Hey guys, welcome to lesson 1 of neural networks from scratch in C++. So in this section, I want to introduce a bit of theory before we get to any actual coding. And we're going to start with something that seems very different from what you'd expect a neural network to be. But in fact, we can construct a neural network from the following equation. So I'm going to start drawing an equation that Canadians know quite well. And that's the equation that converts Celsius into Fahrenheit. So F you can think of for Fahrenheit, and it takes in the input C, which is the degrees in Celsius. And the equation is 9 over 5C plus 32. So most people know the approximation. You just multiply by 2 your degrees in Celsius and add 30, which is a pretty good approximation for the most part, but this is the actual equation. Okay, so why did I even draw this equation? Well, we're going to construct a neural network diagram from this equation. So you don't even know exactly what a neural network is, but we're going to start building one piece by piece. So I'm going to make a circle over here. And here I'm going to put C inside the circle. Okay, and I'm going to make another one over here. I'm going to put F in it. And now I'm going to draw an edge, specifically a directed edge. So it's an arrow that starts from C and points to F. And what we just did right now was we created something called a weight. So this here, I'm going to assign a value of 9 over 5. And this is our weight. So now you know a very important term that you see quite commonly in neural networks. So that's the concept of weights. So what this weight is it's saying that we take our input C, and this is the amount that C contributes to the output F. So 9 over 5 is the amount that we multiply by C, and that is how much C contributes to this output F. And we're missing another input, obviously, because yes, C contributes by being multiplied by 9 over 5 by this weight, but we still need to introduce this plus 32. So you might notice that, well, C is an actual input into this function, but this 32, it's not being multiplied by something that comes from the real world, like data that comes into the function. This 32 stands here by itself, irregardless of what the input to the function is. So if this was 0, C was 0, this term would disappear, and you'd be left with just the 32, right? So that's why we end up calling this input an actual user-provided input. We call this a feature. So this is a feature that contributes to the output, so that's what we're going to call these. But now I'm going to make an artificial input, and I'm going to put in the value 1. And just like our weights, they multiply these input features, we're going to make another directed edge, which looks very much like a weight, and we're going to assign it 32. And as you can see, that this artificial input 1, if I were to rewrite the equation like this, you could think of it as this as like a kind of like an input. I just wanted to draw this multiplied by 1 so you can see how it fits into the neural network diagram. So it doesn't come from the real world. It'll always be there, a 1. But the idea of you multiplying the input by this weight, the same way that you do it with the features, is the same. The only exception is that we don't call this number a weight. We call this something else. We call it a bias. So weights, they multiply features, and biases are kind of independent. They don't care about the data that comes from the real world. They're just kind of constants that are added to our equation. And if you remember from high school, the equation y equals mx plus b, so the equation for a line. Well, this m, we called it slope. In our case, we're now calling it a weight. But it's great that the equation was mx plus b, because now you can think of b stands for bias. So that's what this 32 term is. So we just constructed a neural network, and you're wondering, okay, so like what is a neural network? Is it just a bunch of inputs and outputs, and we multiply these inputs in specific ways to produce the output? In a sense, yes, we'll get more specific, but we're just slowly building some terminology. So let's kind of do a bit of a recap of what you've learned. So we just drew the equation for converting Celsius to Fahrenheit, and we tried to map this into a neural network. So the way that you make neural networks is you make these circles that represent features, or these, I guess, artificial features, and you plug in the particular datum that corresponds to this particular feature. So in this case, this feature is the Celsius feature, and over here, this is the Fahrenheit output feature. And then we made directed edges, so it's always left to right, and we assign these directed edges with either weights or biases. The functionality of the weights and biases is the same. It's just the one difference between them is that weights, they multiply like user-provided features, and these biases, they just multiply these artificial ones that we created just to stay consistent with our drawing. Okay, and I mean, I didn't say it explicitly, but you can think of if you were to map like what's going on here as an equation, it's pretty much you multiply the inputs by these corresponding weights and biases, and then you add them up, right? So if I were to multiply this weight by c, and then 32 by 1, so just 32, add that up, you end up getting this f of c back. Okay, great. Now I need to quickly introduce a mathematical structure that you're going to be using quite frequently in your study of deep learning. And I need to introduce this now because everything that follows is going to be using these things that we're calling vectors. So I'm going to go to the right, and I'm going to introduce a new method of drawing the exact same equation. So you might be wondering why. Well, when we're talking about deep learning, this is a very simple one, as you'd expect. Like, obviously, the very first introduction to drawing neural network diagrams is going to be a very simple equation that we can convert to a neural network diagram. But neural networks, you'll find for particular reasons that they consist of many, many different equations, and combining those equations together in interesting ways. So these vectors and the operations on vectors, and when we get to later videos, matrices, which you can think of as sets of vectors, operations on vectors are very compact, and it's very easy to represent vector arithmetic, or I guess linear algebra, that's the proper term. It's easier to represent that for a computer, for an actual program to do this type of math. So I know that's a bit vague now, but you're just going to have to take my word for it. Okay. So what is a vector? For our purposes, a vector is a list of numbers. There's a mathematical definition, a very strict mathematical definition for vectors, which this is definitely not at all that definition, but for our purposes, it's good enough. So a vector is a list of numbers. So we can either have vertical or horizontal lists of numbers. So let me make a vector, 1, 2, and 3. So here is a vertical list of numbers, or you can also think of it as a column, and that's why we call this a column vector. So I'm just going to put col here. If I were to flip this on its side and have 1, 2, 3 like this, this is a row vector. Okay, great. So now, there is an operation on vectors that we call the dot product, okay? So let's say that I had a vector v equals, well, let's just stick with 1, 2, 3. Let me fix that 3. And I have a vector g. And by the way, this arrow notation, this is how you know that if you have a variable. If I gave you just v without you knowing what's in it, and I put an arrow over it, you'd know that it's a vector. Okay, great. So I have another vector, and I'm going to put in 4, 5, 6 into this one. And now there's an operation called the dot product. So if I do v dot, and it's great that it's called a dot product because it's very easy to remember this is what it looks like. It kind of looks like multiplication, but when you're doing it between vectors, this is known. Like you're never gonna, this means that it's a dot product. Okay, so the way that you compute the dot product is you multiply the values term by term in the respective vectors. So 1 is the first element in the v vector, 4 is the first element in the g vector. So you multiply those up and you store that result over here. You can think of it as like storing a partial result. And let's now multiply the next, so 2 by 5. So now we're going to store 10 as another partial result. 3 by 6, so that's 18. And then when you're done storing all the partials, you add them up. Okay, so what would this be? This would be 14 plus 18. So that would be 32. And this is the result of your dot product. So why on earth did I bring up this notation? Well, it's very compact. You can see that if I have 2 different lists of numbers, I just need to do dot, but like this, do this dot product to pretty much unify all of these lists into one final number. So why is that important? Well, let's try to actually convert the previous equation into a dot product. Okay, so I'm going to make a let's call the, I don't want to call the inputs f because that'll confuse you for Fahrenheit. So let me just make arbitrarily choose x as my input. So let's say x is the data that comes from the real world, or just like the, let's make it the input vector. So what are our inputs? Well, we have the actual input c and then this constant 1, right? So I'm going to make a vector c and 1. And you might be wondering, like, where do row vectors come in? So far, we've just been working with column vectors. Well, I'll get to that in a bit. So here we have x equals c, c1. And now let's have a new vector that represents our parameters, so the weights and biases. So I guess parameters p. And this is equal to 9 over 5. And 32. So now you might see what would happen when we take the dot product between x and p. So if you don't see it, try it out yourself now. I'll give you 2 seconds, maybe pause the video. Okay, so remember we multiply term by term. So I'm going to, you might notice like if I did x dot p or p dot x, it doesn't really matter. The output would be the exact same, right? Because multiplication doesn't care about the order of the data, okay? So I'm going to, I'll just assume that I'm doing it from left to right, just to show my steps. So here is 9 over 5. And then remember, we get the next partial. So 1 times 32. And then add this up. So I'm going to add up, but I'm also going to simplify and just rearrange. So I'm going to make the 9 over 5 be the first term, and then c, plus, and I'm going to drop the 1 and leave the 32. And this is the exact same equation that we had before. So now this is just in dot product notation. So as long as we have some data structure that represents the inputs and another data structure that represents the parameters, there is a way to unify them to represent a linear equation. In this case, this represents f of c. And this is all represented as one dot product. So now you might be wondering, like, how is this useful? Well, in neural networks, we have these things called weights and biases. So those are, you might have a neural network that you train through some procedure. So you're tuning the neural the weights and biases to end up being particular values that that give good outputs. So I'll go into that process of how neural networks are trained in a later video. But when you finally have a trained neural network, you just have, and it's going to, I mean, yes, we showed this simple one, but you can try to extrapolate from this that neural networks, they're some sort of set of parameters, so weights and biases, and there's going to be some other stuff that comes later as well, but in essence, that's what they are. And we can store that data in some vector, and say we want to run inference on a model. Well, inference being in the real world, we put in data and we get some outputs. Well, the data, this is coming from the real world. It could be coming in real time. It could come from some data set on disk. But this is a way to essentially separate the parameters from the data. You have like one object that represents the parameters, one object that represents the data that's coming from the real world, and then through a very simple operation, we can essentially unify the two to produce an output. Okay, hopefully this wasn't too overwhelming. We're going to add on to this study of vectors by looking at matrices, which they're nothing special. They're just an extension of vectors in the next video. And then finally, we're going to start programming after we have a bit more foundation. Okay, see you in the next video.